Hi everyone, I'm Ye Chang, and I'm a member of Artist Red community. As a embedded AI engineer, I'm glad to be here to share some experience on using AI in Artist Red OS. So let's start this presentation. Please give me 1 minute to share my presentation. Okay, so let's start this slide. So the title of my presentation is How do the embedded software engineers harness large language models in AI era? So in this slide, we can see that the left side of the slide displays some blue points representing CNN-based AI models such as VGG, AlexNet, ResNet. The green line depicts a typical increasing trend of CNN-based AI models. In construct, the red line here, and the red line depict the typical deep increasing trend of transformer-based AI models. To further demonstrate the state of the embedded engineering in the AI era, we observe the right side of the slide, where the computing power gap between the AI computing requirements and the embedded engineering continues to be widened over the time. So for our embedded engineer, are we truly confined to the CNN phase in the new AI era? I think the answer is both yes and no. So to address this question, we can begin by seeing the history of large language model development. Here is the picture as depicts in the upper part of the slide. Prior to 2021, large language model developed at a low pace, but after 2021, its development accelerated. Now, I think there are over 200 large language models around the world. Large language models has undergone 5 stages. We call it cores, props, embeddings, chains, and agents. The first 4 stages are not relevant to us, I think. Here is those 4 stages. But the second stage presents a valuable opportunity for our embedded software engineers. For instance, as mentioned by Microsoft paper, I think it's published in last year. During the agent stage, large language model can provide thousands of APIs for users, particularly for device APIs, which are closely related to the hardware and thus have significant implications for our embedded software engineers. Here is the device APIs. We can use these APIs to control some hardwares. And also we can explore the opportunities from the viewpoint of the application-oriented. In the field of large language model, there are two significant research aspects. The first one involves training and designing large language models, which is primarily dominated by large companies such as OpenAI, Google, and Microsoft. Those companies are really rich, so they can use a lot of money on training and designing models for large language models. But it is very hard for our companies, like small companies or university research teams. We can't afford it. Therefore, this path seems it's very hard to do for our embedded engineers. Another approach is use large language models in different applications, such as such as smart home, robot, manufacturing, and auto driving. These domains share a common characteristic is hardware related. It's as they involve interactions with various devices. For our embedded software engineers, the focus should be on how to enable smart functionality across all these devices with RT-Thread OS. We predict that in the near future, the majority of IoT devices in our labs will become increasingly intelligent, such as refrigerators, washing machines, and air conditioners. And they will become more and more understanding the human beings. The most important function among them is to interact with human beings. However, the AI computing power requires for this functionality account for over 95% of entire device AI computing power. The actual IoT device-related function only account for 5% of the total AI computing power. So relative to the intelligence of IoT device, the human-machine interaction function seems necessary, but at the same time, it is very wasteful. Therefore, there are two main design measures for the intelligence of IoT device. We call it independent AI and distributed AI. For independent AI, this is independent AI. Each IoT device maintains separate AI functionality. That human-machine interaction and IoT device functions are deployed on the same chip. The main problem with this design is the high cost of individual of each IoT device. The second problem is, although human-machine interaction is a necessary function for each IoT device, but it consumes a significant amount of AI computing power resource. Another better approach, we can call it a distributed AI, where we place all human-machine interaction functions in a central computing node and locate each individual IoT device functions to a separate chip, just as the picture here. with this design, I think the benefits of this method are very clear. So the first one is it is cost efficient. And secondly, because all devices have human-machine interaction functionality, so the device have very high AI computing efficiency. Here is full distributed AI design. The entire software architecture consists of three components. The first one is the central computing node. And the second part is the communication node. And the last one is the distributed control node. The central computing node uses large language model for human-machine interaction, and it's programmed by using Python. It can employ various models such as Llama, ChatGPT, ChatGLM. The communication node use methods like ROS, DDS, and Wi-Fi to facilitate information exchange, transmitting the natural language processing result to the target device. Finally, in the distributed control node, the AIOS module of Artist-Red OS is used to parse and execute received instructions and control logic. Throughout this process, the central computing node requires substantial AI computing power, while the distributed control node do not have have constraints on AI computing power. So this software architecture is very flexible. And here is the demo. As the in this test, we use STM32 series MCU as a controller of distributed controls node, and NVIDIA GPU as our central computing node. In order for a large language model to understand users' commands, people need to pre-record the detailed information of the commands into large language model. We can achieve this API by writing a JSON file to help a large language model understand the functionality of my commands. For example, if I want to open a LED light, I need to inform the large language model of the function's name and its specific functionality. During the process of human-machine interaction, large language model will then know that it can open the LED by calling this function. Then it can control the Artist-Red board. Okay, so this video on the left side demonstrates the human-machine interaction process. We request the large language model to search for a song, then print the lyric of the song, and then flash the LED in this sequence. Throughout the entire process, we avoid the traditional calling process and instead using a large language model to consecutively call the RGB LED on function 26 times. Okay, we can see here is I told the large language model to sing a song. And here is the reaction of the large language model. It will cost a long time to compute computing. Here is the large language model called the Artist-Red APIs 26 times. Here is the call process, calling process. And at the same time, we can see the red side, the corresponding LED flashing process is depicted. The entire process was smooth and seamless. Here is the song, like do, re, mi, fa, sol, la, si. Okay. And if we want to access more APIs to make the large language model understand, we need to go back to the previous step and write more APIs just like this. In the last demonstration, we just use RGB LED on function to call tell the Artist-Red test board to flash the LED light. But if I want to use 3 functions, just like RGB LED on, RGB LED off, and this is delay. We can use these 3 functions to flash the LED light, just like the demo before. But the whole process will be very complicated. Okay, so here is the conclusions and the future work. For the conclusions, the first one is the distributed AI is a better way to develop the embedded AI products. And the second is Artist-Red OS can help embedded software engineers easily design new AI products. And the last one is with large language models, Artist-Red OS can execute complex function clusters without coding. And for my future work, I think the first one is I need a better large language model for better understanding the Artist-Red OS. And the second one is I need more Artist-Red AIOS APIs to control hardware. And I also need OTA for update the AIOS APIs for Artist-Red OS. So that is my presentation. Thank you.
Thank you so much, Yi. That's very, very interesting indeed. I've not done any work at all with large language models, just very low level AI models. But I think you're right. There's going to be an increased demand for this sort of thing in the very near future. So I'm going to be very interested to see how this develops. Oh, it's very strange because you're still sharing your screen and I'm on it. So yeah,
I'm not sure. Yeah, pardon?
I don't know. I think you can click the stop share button. So Kathy's posted a question saying that she's curious if there are any embedded engineers who've already been involved in projects requiring AI integration. And I think that's just general AI, not necessarily large language models. I'm actually working on one myself at the moment. Let me post a link. On the one hand, it might sound a little bit silly. I've decided to create a timer that counts down to my 100th birthday party. And I'm using an old display technology called vacuum fluorescent displays. There's a picture in the link that I just sent. The problem is that it's 33 years until my 100th birthday, but these display tubes have only got a lifespan of about 10 years. So if I had the countdown timer constantly counting down, in 10 years' time, the tubes would wear out. So in 33 years' time, the counter would be dead. And so the solution is to add a little bit of AI. So there'll be a camera and a small AI-powered microprocessor. And the AI will know when somebody is looking at the display. So it's only if somebody's looking at the display that the tubes will light up. If nobody's in the room, or even if there's lots of people in the room, but everyone's looking somewhere else, the display will power down. And although that might seem to be a fairly trivial application, it's actually, it could be useful for a lot of things. There are a lot of displays all over the place that are on all the time. Even when you walk through a supermarket and the big refrigerators, and they've got motion detectors, so the lights come on just if you walk down the aisle. But the possibility of having it recognize if somebody's looking at that particular refrigerator, that's when the lights come on. So I think it won't be very long, only a few years, before AI is empowering absolutely everything, all the embedded systems around. So I think the work you're doing is very timely and very important.
Okay, thank you.
So Khalid says, I worked on object recognition on ESP32. That's interesting. What was the reason for it? What were you trying to? Was it for a robot or some other application? If anyone's got any questions at all for Yi, please do post them here. And Yi, if you could stay on for a little bit and keep your eyes on for any questions and answer them if they come up, that would be awesome. Okay, so the third talk in this